Okay. All right. They can be pretty tough. The only thing I can say is you really need to know those 11 trig identities very well.
Okay.
So why don't you give me some? Let's go through some of them.
All right. So just to refresh, the first one is cotangent of 5/7. Cotangent equals 5/7.
Hold on. Didn't hear the equal sign.
Sorry. So cotangent of theta equals 5/7. Then find tangent of theta.
All right. Whenever they give you one trig function's value, it actually allows you to calculate all other 5 trig functions. At least it does if they give you the correct quadrant. Now, they didn't give us a quadrant here, and the reason is they're asking you about tangent. So whatever the sign on tangent, cotangent is, has to be the same sign on tangent. Well, remember, the first thing to do is to draw a triangle and label either theta or x. Now, dimension that triangle as much as you can for me.
I can't think of the name right now. The bottom side would be 5.
That's the adjacent side.
The adjacent side. And the hypotenuse would be 7.
Not the hypotenuse. The opposite. Here, remember what tangent?
Oh. Okay, cotangent.
Tangent is opposite over adjacent, therefore cotangent is adjacent over opposite.
So cotangent 7/5.
No, they gave you cotangent. They told you
tangent 7/5.
Yes, tangent is 7/5. Now, you could have just done that knowing that tangent is the reciprocal of cotangent. But this is such an integral process on the type questions you're starting to give me that I want to make sure we do it every single time. This is like the quintessential trig question, where they give you the value of one trig function, and they tell you which quadrant it's in, and then they ask you what the other 5 trig functions are.
Okay.
All right, what else you got?
The next one is if cosine of x equals 1/6 and sine of x equals √35/6, then find cotangent of x.
Yeah, this is a more traditional problem. Now, they've given us, what's the first step?
Finding tangent?
No, draw a triangle.
Oh, draw a triangle.
Label X. Okay. Always, that's always the first step. That makes the problem so easy, it's unbelievable.
Okay.
You have to draw a right triangle, and you have to label X, because there's 2 angles here. There's this one on the lower right. There's also the one at the top. So if we don't label X, we can't dimension the triangle properly. So based on the information they gave us, that the cosine of X was equal to 1/6, tell me how I can dimension this triangle immediately.
The adjacent side would be 1. The opposite side would be √35.
Hold on for a second about that. Let's just do it based on that.
Okay, then the hypotenuse would be 6.
Okay. Now, the Pythagorean theorem allows you to come up with that's √35. Okay. The biggest reason they give you this information on the right is to tell you what quadrant it's in. In other words, we could figure out what the sine of x was if they just told us what quadrant it's in. So this wasn't particularly helpful, except it does tell you what quadrant are we in. Where is the cosine positive and the sine is positive?
In the first quadrant?
Yeah, that means cotangent's going to be positive also. Because all trig functions are positive in the first quadrant. But these are the two pieces of information they give you. They give you the value of one trig function, which allows you to dimension two sides of the triangle, and then they tell you what quadrant it's in. It wasn't so much that they told us that the sine was equal to something, it's that they said the sine was positive. And the fact that the sine is positive, there's only one quadrant where both cosine and sine are both positive, and that's first quadrant. And that tells us that the cotangent is also going to be positive.
Okay.
What's the cotangent?
The cotangent is going to be 1 over root 35.
Okay. And you're fine with not rationalizing the denominators?
Yeah. Mm-hmm.
Okay. I like that a lot. All right. What else you got?
The next one, if cosecant of x equals 7/3, and cotangent of x equals 2 root 10 over 3, then find secant of x.
First step?
Draw a triangle.
You got it. That's always going to be the first step. And don't forget the most important part almost. Label x. Because it can change everything if I decide. There'd be nothing wrong with me labeling x up there. That's perfectly fine. I'm still going to be able to dimension the triangle. But I've got to label x as a reference point. I typically always put it in the lower right, but there's no rhyme or reason to that. I could just as easily have put it in the top.
Mm-hmm.
The cosecant of x equals 7/3. What two sides can I dimension?
You can dimension the opposite side and the hypotenuse.
Okay, what's the opposite side?
3. And the hypotenuse is 7.
Okay. Now, we don't need the value of the cotangent. What we need is its sine. In other words, we need to know which quadrant they're talking about. Again, if cosecant is positive and cotangent is positive, they didn't even need to give us this. They could have just said it's positive.
Mm-hmm.
That puts it, again, in the first quadrant. Now, in terms of, we do need to solve for this other side. But we can do that on our own. We don't need their cotangent value. What's this other side based on the Pythagorean theorem?
49 minus 9, so square root of 40?
Yeah.
And that would come out to 2 root 10.
2 root 10, okay. Now we got our triangle fully dimensioned, and we know what quadrant we're in. We could answer all other 4 trig functions. But secant, we know it's positive because it's first quadrant. What's it going to be?
7 over 2 root 10.
Yeah. And if you do every one of these problems like this, you'll be fine. And a lot of times they won't give it to you like they're doing it here. They'll say theta is between, they might tell you this, x is greater than or equal to 0 and less than or equal to pi over 2. Okay, that is enough information to know you're in the first quadrant, which is all we need to know. We did not need to know what the value of the cotangent was. We just needed to know whether it was positive or negative.
Okay.
And what else?
Okay.
These are not actually verifying trig equations.
No, it gets into it.
Okay.
Yeah.
Good. Okay. These are traditional. Like I said, if you were testing somebody on trig knowledge and you could only ask them one question, this would be it.
Okay.
The ones you're doing right now.
Okay. The next one. So for find the value of each expression using the given information, secant of theta and cosecant of theta. Okay, so that's what it wants to find, secant of theta and cosecant of theta. And tan of theta equals -5. And cosine of theta is above 0. And it's not cosecant, sorry, it was cosine of theta is what they want to find. I read that wrong.
Like that?
Yeah.
Okay. First step.
Draw a triangle.
And?
Label what we can.
Well, label theta.
No, theta.
Okay. If you don't label theta, you're not going to be able to dimension this triangle. You've got to label theta. Okay. Now, based on this triangle and the fact that the tangent of theta equals -5, what two sides can I dimension?
The hypotenuse, or no, the sine and cosine. So
What's tangent? What's tangent equal to?
It's opposite over adjacent. Sorry, the opposite side and the adjacent side.
Okay. That allows us to label two sides. What are they?
The opposite side is -5.
Well, let's forget the negative sign for a moment.
Okay, so the opposite side.
First of all, the reason I'm going to forget it is because you cannot have a side of a triangle be -5.
Yeah.
Okay.
That's true.
So I always deal with the absolute values. Once I figure out what quadrant it's in, then I know what the sign on these two functions is going to be. And that's the way to go about trig. Leave the sign till the end. And by sign, I mean plus or minus sign.
Okay.
What's the adjacent side?
1.
Okay. What's the hypotenuse?
The root of 26, square root of 26.
And now going up to that information combined with that information, what quadrant are we in?
We are in the 4th quadrant.
Good. That's all we need. Notice they didn't give us the value of cosine of theta. They just said it was greater than 0. That allows us to figure out what quadrant we're in. Okay. So secant of theta, what's the absolute value of it? Forget the sign for 1 second. Just what is the absolute value of the secant?
Root 26 over 1.
Now, the fact that it's in the 4th quadrant, what is its plus or minus sign?
It's positive?
Yeah, because it's the reciprocal of cosine. So what's the cosine of theta?
1 over root 26.
Yeah.
Okay. Okay, I have one more of those, and then it gets into the proofs.
Okay.
The next one, it wants to find cotangent of theta and secant of theta. And sine of theta equals 1/3. And tangent of theta is above 0.
Greater
than 0.
Okay.
Or no, tan of theta is less than 0. Sorry.
All right. First step.
Draw the triangle. Then label where theta is.
Now, this time I'm going to lay the theta up there just so you can see that it doesn't matter.
Okay. Now we can label the opposite side in the hypotenuse. 1, yeah, and 3.
What's this side?
The square root of 8.
Which is 2 root 2.
2
Okay.
root 2. Okay.
And what quadrant are we in based on that piece and that piece?
Second quadrant.
Good. That's all we need to proceed. What's the absolute value of the cotangent of theta?
2 root 2 over 1.
What is its sine in the second quadrant?
Negative.
What's the secant of theta?
Secant of theta equals 3 over 2 root 2.
What is its sine in the second quadrant?
Negative.
That's how you do these. It's as simple
Okay.
as that. And every single step we took, that's the way I'd like to see you do them all.
Okay.
In other words, draw the triangle, label theta. Doesn't matter which angle you want to label. And with that second piece of information between the first piece and the second piece, you can always figure out the quadrant, figure out the absolute values first, put a sign on it second, and you can't go wrong with that technique.
Okay. Okay. The next one is simplify the expression.
Okay?
So cosecant of x times secant of x minus tangent of x.
That's it?
Yeah.
Okay. What's cosecant of x in terms of, usually when they want you to simplify, you can't go wrong by turning everything into sines and cosines. Okay? This is one step short of verifying. But when you get into verifying, in other words, if there was a right side to this, then you know which direction you kind of have to go. But if they just are having you simplify an expression, then just turn everything into sines and cosines. First of all, recognize that I can turn that into sine, I can turn that into cosine, and I can turn that into sine over cosine. So that should allow us to simplify this greatly. So what's cosecant?
1 over sine.
What's secant?
1 over cosine.
And what's tangent?
Sine over cosine.
I think for a minute now. If I had to find a common denominator, so this is what we got. We got 1 over sine x cosine x minus sine over cosine. Now, if I had to subtract those two fractions, how would I do it?
Find a common denominator.
Which is going to be?
Sine x cosine x cosine, is it cosine squared or is it just cosine x?
Cosine. In other words, a common denominator merely needs to be divisible by each denominator evenly. So that is my common denominator. Now, over here, I didn't change it, so I still got a 1 in the top. What do I have over here? What's the same as that fraction right there?
Isn't sine x cosine x, or
No, that would make it 1.
sine x squared?
Yeah, sine squared x.
Sine
That's the
squared.
difference. Sine squared x is not the same as sine of x squared. And by that I mean this. Sine squared x is not the same as sine of x squared. It is the same as sine of x in parentheses squared. But these two things mean totally different things.
Okay.
Okay? Now, the beauty of what we just did was it turns the numerator into 1 minus sine squared, right? So this comes down to 1 minus sine squared over the common denominator, sine x cosine x. And using your trig identity, what is 1 minus sine squared equal to?
Cosine squared.
And now we can do a lot of reducing. We can cancel that cosine with one of those cosines. We end up with cosine x over sine x, which is equal to what?
Cotangent x.
That's what the whole thing simplifies to, cotangent x.
Okay.
When they ask you to simplify these, generally you're going to be able to bring it down to one term. Not always, but generally. In other words, they make it so that it's nice. If you know what I mean by that. They're giving you a rather complicated expression, and it's going to come down to a single trig function. And this is kind of the lead-in to verifying trig functions. This is the same process you have to do when you verify trig functions. In other words, they could have just as easily, if they'd have wanted to, they could have started this problem out by saying, let's make that equal to cotangent x and verify that. In other words, they wouldn't have given you any of this. And the problem would have said, verify that the left is equal to the right.
Okay.
And we would have done exactly the same thing that we did.
Okay.
Okay. All right. What else?
The next one is secant of x times cotangent of x minus sine of x.
I don't really mind this method that they're introducing you to, because the solution to this almost always involves turning everything into sines and cosines. And that is the solution of last resort when you are doing verifying trig identities. Is if you can't figure out how to do it, turn everything into sines and cosines and go from there. Well, on these halfway problems, I guess I would call them, because they don't tell you what it's supposed to be equal to on the right side. Let's just go ahead and do that. What's secant of x equal to?
1 over cosine x.
And cotangent of x?
Cosine x over sine x.
Minus sine x. Okay, what's that equal to?
Cosine x over cosine x times sine x.
Cancel whenever you can as your first step.
So that just becomes sine x?
It's 1 over sine x.
Oh, 1 over sine x.
Right? In other words, if I'm canceling that with that, I'm left with a 1 over sine x. Okay? Now, I could turn that into cosecant x, but that's not going to help things. In other words, my goal was to turn everything into sines and cosines. Well, let's try to operate on this. Rather than turn the left, if I turn the left into cosecant x, I got nowhere to go.
Uh,
If I leave everything in sine, well, I can combine these two. What's the common denominator?
wouldn't it just be sine x?
Huh? What goes over here?
1
Goes here?
sine x.
No. Notice the reason I do it this way is because I can instantly check
Oh,
that is not equal to sine x. So whatever I put in the numerator has to make what I circled equal to sine x. That's
so that would become sine squared x?
correct. And you can instantly tell whether you've made a mistake or not. Rather than doing the thing the way other people might do it, if we do it this way, then you instantly know, well, I haven't changed that. That's correct. And that is equal to that. So that's correct.
Mm-hmm.
And now, when I combine those two fractions, because I can now do so because they have a common denominator, what do I get?
1 minus sine squared x over sine squared x.
Just sine.
Just sine?
Well, we're subtracting. We're not multiplying.
Oh, okay.
When you subtract or add fractions and they have a common denominator, the denominator doesn't change. Because all you do is operate on the numerator. In other words, if I have 2/6 minus 1/6, the only thing I do is operate on the numerator, I get 1/6. I don't multiply 6 times 6 to get 36 on the denominator.
Okay, yeah.
Okay? So always remember, subtraction and addition is actually much harder than multiplication. Multiplication and division is a piece of cake compared to addition and subtraction. When you add and subtract fractions, you've got to find a common denominator. When you multiply, all you do is multiply numerators, multiply denominators, you're done.
Yeah.
Okay, now what is 1 minus sine squared x? And learn to recognize this because this is what you're most likely to encounter. In other words,
Cosine.
remember when I said this is the identity, but this is never what they give you. It's too easy. They almost never give you a problem where you can narrow it down to sine squared plus cosine squared. They give you an alteration of that. And the alteration they've given you is 1 minus sine squared. So what is that equal to?
Cosine squared.
Now, I don't know that we necessarily have to do this, but I guess I would. Turn that into cosine x over sine x times cosine x. And the only reason I might do that is because there's an identity for that, which is cotangent. So this might be their answer. But it could just as easily be that. In other words, notice I got two terms regardless.
Mm-hmm.
I think you could make an argument that this bottom circle is no more simplified than the top circle. So this is where verifying trig identities is helpful because they might have put this on the right side. They might have put that. You could deal with either one of them.
Mm.
You know what I'm saying?
Yeah.
Yeah. I don't know which is the right answer. Either one of those is correct, but what they're looking for, I'm not sure. I'm guessing the bottom one is probably what they're looking for an answer. But the beauty of these problems are actually tougher than verifying trig equations, because with verifying trig equations, they give you a right side of the equation. In other words, the right side would either be that or this. My guess is it's going to be this.
Okay.
If they were to put a right side in there and say, prove the left side is equal to the right side. And that's a typical problem. I'm not sure I like what they're doing here with you, but go ahead.
Okay, 20. So this one is cosecant of x. Cosine of x minus cosine of x times cotangent of x.
Okay. Again, I would prefer to have a right side just so we could know what we're shooting for. Without a right side, I see the solution to all of these as just convert everything you see into sines and cosines. And maybe that's the purpose of this exercise, is to show you that that is a tried and true method of verifying trig identities. It's just that there's some trig identities that don't have any sines and cosines in them, and it's really a much harder way to verify them by turning everything into sines and cosines. So that isn't always the correct way to do things when you're verifying trig identities. But it's not a bad way to start, especially if you see any in the equation. In other words, I'm looking at a cosine x there. So, okay, let's turn everything in. In other words, it would be different if I had the following. Secant squared of x minus 1 equals tangent squared of x. Okay? If I was trying to verify that identity, I'd be foolish to turn everything into sines and cosines. Right? It's going to make it much harder. I would have to then find a common denominator on the left. I would have to switch this tangent into sine squared over cosine squared. It would just be ridiculously much harder. Whereas if I know my Pythagorean identity, I know that secant squared x minus 1 equals tangent squared x. So in one step, I verify the thing. Whereas if I had to turn everything into sines and cosines, it might take me 3 or 4 steps. So just a note on that is that when you're actually verifying trig identities, it's not necessarily correct to turn everything into sines and cosines. But if they just give you an expression, not an equation, then I would say, okay, pretty much always just turn it into sines and cosines and proceed. So what is cosecant x?
1 over sine x.
Okay, I'm going to leave that as cosine x. What's cotangent x?
Cosine x over sine x.
Whoops. So we have a common denominator. So the top becomes what?
1 minus cosine squared x.
Bottom?
Sine x squared.
Just sine x. We're subtracting.
Oh, sine x, yeah. Sorry.
We're multiplying. If we're multiplying, it would be sine squared x. And now what does the top become?
Sine squared x.
Bottom is sine x. So the whole thing becomes sine x. That's your answer.
Okay.
And if this would have been an identity, that's what would have been on the right side. It would have been like that. Okay? And then they would have merely said, prove the left side is equal to the right side. And I would have still taken the exact same tactic, but I would have been more certain of it. In other words, the more sines and cosines you see in your original identity, the more likely the solution lies in turning everything into sines and cosines. If you see nothing but tangents and secants and cosecants and cotangents, then it may not be the best way to proceed, turning everything into sines and cosines. But when you're just given an expression, it probably almost always is.
Okay. Okay, the next one is tan of x plus sine of x times secant of x, all divided by secant of x times cotangent of x.
All right. Again, notice that every single trig function can be turned into sine, cosine, or cosine.
Oh, on the bottom one, it's actually cosecant of x and tangent of x. I read the wrong problem on the bottom. Sorry about that.
All right. In fact, I say that's all right. If you want to drive a student crazy, give them a trig identity and make a typo on the left side. Well, and the reason is that you can spend 30 minutes trying to prove that thing, and you're never going to prove that it's equal to something that they've said it's equal to.
Mm-hmm.
You know what I'm saying?
Yeah.
In other words, whatever this is equal to, once we solve it, if they'd have put something over on the right side that wasn't that, I would literally spend a half an hour trying to prove it. And I've had students give me trig identities before that I couldn't solve. And after I ended the session with them, I spent half an hour trying to solve it, and I never could solve it. And I finally came to the conclusion that the student gave me a typo. In other words, he told it to me wrong. And if you get it told to you wrong, you're never going to solve it because it's not an identity. So the one advantage of doing it the way they're doing it with you is that we can always simplify this. We might be able to simplify it to multiple things, but we can always simplify it. Okay? By turning everything into sines and cosines. So what's the next line?
The next line would be cosine.
What's tangent?
Of, oh, sorry, sine of x over cosine of x.
Okay.
Over cosine of x
Well,
plus.
you don't need to change that, but what's secant of x?
Yeah. 1 over sine of x.
1 over cosine. Remember, their first letters have to be different. That's the way to distinguish. You know that the reciprocal of secant cannot be sine, because they would both start with s. The reciprocals always have to have different starting letters. That's the way you guarantee you have it. Okay.
Okay.
Bottom, what's cosecant x?
1 over sine of x times sine of x over cosine of x.
Actually, cotangent is cosine.
Oh, cosine of x over sine of x. Dang it.
Right. Okay, well, we got a bunch of common denominators. Well, we don't need one in the bottom because they're being multiplied. But what's the top become?
The top becomes sine of x squared.
Not squared. You're not multiplying. You're adding.
Oh, sine. No, 2 sine x?
Yeah. Over the common denominator.
Over cosine x.
Now, in the bottom, what do we have?
Cosine of x over sine of x, or sine squared of x?
Right. In other words, we are multiplying in the bottom. Okay, well, here we have the typical fraction divided by a fraction. So what are we going to do?
I'm unsure.
Flip and multiply.
Flip and multiply.
All division problems can be done as multiplication problems, whether you're dividing by a fraction or not. But when you have a fraction, in other words, if I have 1/3 divided by 1/4, I am never doing that as a division problem, ever. I'm going to flip the bottom and multiply so that it becomes 1/3 times 4 over 1. Okay? So whenever you see a fraction over a fraction, always flip and multiply. So if I do this, I now get, let's see, the numerator, we're going to have 2 sine to the third of x. And the denominator, we're going to have cosine squared of x. You see? Now, again, that might be a final answer, but I can separate it into 2 sine squared of x over cosine squared of x times sine of x, and that is tangent squared. So my final answer might look like this. In other words, there are multiple answers for these problems you're giving me.
Okay.
Okay, this could be an answer, nothing wrong with that answer, but that's the same as this answer over here. So the reason they do verifying trig equations is so you don't have to make that decision. In other words, whichever one they would have put on the right side of the equation, that would have been there, and then you could have worked towards that.
Okay.
I'm not sure I'm that fond of what they're doing here, although I kind of see its purpose. It's what we're really doing on every single problem is turning everything into sines and cosines. And like I said, that's not a terrible strategy for verifying trig equations. It's not always the most efficient, but it generally works.
Okay, the next one is 1 minus sine squared of x, which I already know equals cosine squared of x.
Okay.
But I haven't changed it yet. And then the bottom, or divided.
I would not advise changing it until you've written out the
Okay.
problem. I mean, you can get kind of in trouble if you try doing multiple steps in one step.
Okay, and then the all divided by cosecant squared of x minus 1.
All right. Whenever you see an expression like that or like this, think your Pythagorean theorem identities. There's 3 of them. You know that 1 minus sine squared x is cosine squared x. What's cosecant squared x minus 1?
Cotangent squared x?
Yeah. And then that's the same. We can definitely simplify this because I know I can turn cotangent into cosine over sine. So that's going to be cosine squared x over cosine squared x over sine squared x. Flip and multiply, what do you get?
Cosine squared x times sine squared x over cosine squared x.
And the cosines cancel.
So it's just left with sine squared x? Okay.
Yeah. And undoubtedly, had they given this to you as a verifying, it would look exactly like this. They would have said 1 minus sine squared x over cosecant squared x minus 1 equals sine squared x. And you would have had to prove that. And you would have done exactly what we did to prove it. But there's not much else they could put on the right side here.
Okay.
If it were a verifying problem. They're clearly giving you an intermediate step, which is interesting. I have not run into very many students that get this intermediate step. Part of me likes it, part of me doesn't.
Okay. The next one is, oh, sorry. The next one is cosecant of x times cosine of x plus cotangent of x, all divided by secant of x times cotangent of x.
Okay. let me just ask you a quick question. Do you have any verifying? In other words, do you have any that are full equations and not just expressions?
Let me check.
Because if you do, I'd like to do a few of them. I think you know how to do every one of these.
I think so too.
Because all you have to do is turn every single term that's not cosine or sine into cosine or sine. And once you do that, then it kind of solves itself.
Okay.
Let's go ahead and do this one. But
okay, and then
if you have any that are full equations, I would like to do some of those before we finish here.
okay.
So cosecant of x is what?
Cosecant of x equals 1 over sine of 1 over sine of x.
Okay, and I'm multiplying that by cosine of x plus, what's cotangent x equal to?
Cosine x over sine of x.
Okay, all of that's over what's secant of x equal to?
1 over cosine of x.
Times cotangent, which is what?
Cosine of x over sine of x.
Yeah, the more I see it, the more I like this. In other words, they're teaching you the foolproof way of doing it. The only thing is, the only thing you have to know to do these are the first 9 trig identities. You don't really need any of the first 8. You don't need any of the Pythagorean. I guess we've had some where you needed the Pythagorean. So this does use all 11. Okay, and what does this come down to?
1 over sine of x times.
Combine those.
Are we? Oh, okay. So cosine of x over sine of x.
Yeah, and I don't really want to write that cotangent because the secret here is to turn everything into sines and cosines. If I turn that into cotangent, I'm just kind of making the problem harder. I'm going to have to eventually turn the cotangent back into cosine over sine.
Okay.
All right, what's the bottom become?
Over cosine of x times cosine of x sine of x?
Well,
or over cosine of x divided by.
Always cancel as the first step if you can. Oh,
okay.
Don't multiply numerators and denominators just because you can. You don't, that's not the first step. The first step is to simplify and then multiply numerators and denominators. In other words, if we simplify, then it becomes 1 over sine x. All right? Now, that becomes 2 sine x over sine x in the numerator. This is almost more a test of your algebra skills than it is trig. See why? You have to know all of these algebra maneuvers.
Yeah.
The only mistakes you've made so far have been in your algebra, not your trig. You've known every single trig identity that I've asked today. You haven't known how to do the algebra perfectly every time.
Okay.
What's this equal to?
Please don't put this on my table. Don't we chop in or like flip it?
Flip and multiply.
So it becomes sine of x, or 2 cosine of x over sine of x.
All right. Here, let me back up a second here. When I flip and multiply, let's write it first of all before we try to solve it.
Times sine x.
Now,
over 1.
what I feel like is you're not seeing the first step here. What's the next thing I can do? Can't sine x over sine x. By canceling, I mean replace it with 1.
Yeah.
This sine x divided by this sine x is always 1. So when I say cancel and I cross it out, I mean replace it with a 1. So the final answer is 2 cosine x. Okay? But what you don't want to have to do is write it like this. You don't want to have to do that. That's an unnecessary step. In other words, whenever you're multiplying a fraction by a fraction, your first thought should always be simplify. And it doesn't matter whether it's trig functions or algebraic functions. If I have something like 35 over 8 and I multiply it by 16 over 7, I'd be foolish to multiply 35 times 16 and divide it by 56. I would need to get a calculator. But what if I divide top and bottom by 7, leaving a 5 there and a 1 there? Then I divide top and bottom by 2, leaving or 8, leaving a 2 there and a 1 there. I got my answer 10, and I didn't need a calculator, and I never worked with a number greater than 35.
Okay.
So very important concept here. Always simplify before multiplying. Whether you're dealing with numbers, polynomials, or variables, or trig functions, it all applies the same.
Okay.
Okay. Do you have any trig equations where they give you a left and a right side?
Yeah.
Give me that one. Let's do at least one of those because we only got like 6 minutes.
Okay. So tangent of theta times cosecant squared of theta minus tangent of theta equals cotangent of theta.
Okay. Now, notice there's no sines and cosines in this. So probably the best method is not to turn everything into sines and cosines. And I'm looking at a cosecant squared. Well, I know there's a trig identity that's cosecant squared minus 1. So the best thing to do is probably factor out a tangent theta and see where it takes us.
Okay.
Okay, so if I factor out a tangent theta, what's left over?
Cosecant.
Again, this becomes as much of an exercise in algebra as it is trig.
Okay. Cosecant squared theta minus 1.
Okay. And I'm going to leave the right side alone. I'm always going to work only with the more complicated side. And what is cosecant squared theta minus 1 equal?
Cotangent squared theta.
Okay. Now I'm trying to prove that that's equal to that. What's the next step going to be? Now, it does help a little bit knowing what the right side is supposed to be.
Maybe factor out a cotangent?
Can't factor out a cotangent. There's only 2 of them. There's 1 squared there. But I can turn tangent into cotangent.
Okay.
Always look to do that. In other words, if I'm looking for this and I know I got to produce this, then let's turn everything into cotangent and see where we end up. Well, that's 1 over cotangent times cotangent squared. What's that equal to?
Cotangent theta.
There you have it.
Okay.
All right, we got time for one more. Let's do another equation.
Okay.
And the reason is because notice how different that problem was from everything we've done. We didn't turn anything into sines and cosines. We factored, and then we used the trig identity to turn that into cotangent squared. In other words, we never once introduced sine or cosine. And there's going to be a lot of these trig equation identities where that's the way you're going to want to go. You're not always going to want to turn everything into sines and cosines.
Okay. Okay. The next one is cosecant of theta minus cosine of theta times cotangent of theta equals sine of theta.
Did I write it correct?
Yep. Yep.
Okay. Well, the first thing I notice is I see a cosine and a sine. So it can't be terribly wrong to start turning everything on the left into sines and cosines. I don't see anything being squared, so I'm probably not immediately, at least, looking at a Pythagorean identity. So what's cosecant equal to in terms of sines and cosines?
1 over sine.
And cosine, I will leave the same for the moment, but cotangent is
Cosine over sine.
right. Now look at how nicely this is going to work out. That's going to turn into cosine squared. And then I've got 1 minus cosine squared of theta over sine of theta. Again, I'm doing subtraction, not multiplication. And what's the top equal to?
Sine squared of theta.
And I got sine squared of theta over sine of theta.
And that comes out to be sine of theta.
Equal to that, yeah. So
okay.
That's not a bad rule of thumb, is if your original equation already has some sines and cosines in it, then you can't hardly go wrong by turning everything else into sines and cosines and just doing the algebra and make sure that you get it right. But if you see squareds or anything, and remember, we didn't have time. Unfortunately, I've got to leave exactly at 4:15. I have a 4:30 appointment that's 15 minutes away.
That's okay.
So the things that are unusual is when you see stuff like this. When you're doing trig verifications.
Okay.
And the reason these are tough to handle is that there's no identity for any of these four. Okay? But
okay.
if I multiply each one by the conjugate, 1 plus sine of theta, I always end up with something that can be reduced to one term.
Okay.
I multiply that by 1 minus sine theta, I get the same 1 minus sine squared theta. I multiply this by 1 plus cosine, I get 1 minus cosine squared theta. Multiply this by 1 minus cosine, I get 1 minus cosine squared. And now notice that every term on the right can be replaced by a single term.
Okay.
So that's why that technique is such a great technique. And there's not much else that you can do whenever you run into one of those four. And not just with sines and cosines, but secant theta minus 1. If I ran into that, well, I would want to multiply it by secant theta plus 1. Why? Because that turns into secant squared theta minus 1, and that I can replace with tangent squared of theta. So it's a little different with the other four trig functions. It's not 1 minus cosine, it's secant minus 1, or tangent minus 1. So whenever you see a trig function minus 1 or 1 minus a trig function, think multiply by the conjugate.
Okay.
Okay?
Okay.
All right. I will talk to you probably next week.
I will talk to you next week. Thank you, Mr. Cohen.
You're welcome. Bye-bye.